Hello student, I am Dr. J. Srinivas, Senior Assistant Professor, Department of Mathematics. In this video, I will explain the general solution of homogeneous higher order linear differential equation with constant coefficient. Linear differential equation are those in which the dependent variable and its derivatives occur only in first degree and are not multiplied together. Thus, the general linear differential equation of nth order is of the form P naught dny by dx power n plus P1 dn minus 1 y by dx power n minus 1 P2 dn minus 2 y by dx power n minus 2 plus Pn minus 1 dy by dx plus Pny is equal to capital X. Consider this as equation number 1, where P0, P1, P2 up to Pn, P0, P1, P2 up to Pn and capital X are either constant or function of X alone. If P0, P1, P2 up to Pn are constant, then equation 1 is called higher order or in particular nth degree linear differential equation with constant coefficient. And if at least one of them is function of X, then it is called higher order or in particular nth order differential equation with variable coefficient. Now, in this video, I will mainly focus on linear differential equation of nth order with constant coefficient. Such equations are most important in the study of electromechanical vibration, electrical circuits, control system, fluid mechanics and heat transfer, structural engineering, etc. To write equation 1 in compact form, we define differential operator D. D stands for d by dx. Then d square is d square by dx square. D cube by dx cube. And d power n is dn by dx power n. Now, by using these notations, the equation 1 can be written as P naught d power n, P1 d power n minus 1, P2 d power n minus 2, Pn minus 1 d plus Pn of y is equal to x, or f of d of y is equal to x, where f of d is P naught d power n, P1 d power n minus 1 up to Pn, that is a polynomial of degree n in D. Now, there is one fundamental theorem for homogeneous differential equation. Before that, I will explain what is homogeneous and non-homogeneous. Now, we have a differential equation of the form f of d of y is equal to x, where f of d is polynomial of degree n in D. If the right hand side function capital X is equal to 0, then this equation is called homogeneous linear differential equation of nth order with constant coefficients, because we assume that each pi belongs to R. And if x is not equal to 0, then it is called non-homogeneous linear differential equation of nth order with constant coefficient. Fundamental theorem for homogeneous differential equation. It is also called or known as linearity principle. Now, what is linearity principle or fundamental theorem for homogeneous differential equation? Now, consider a differential equation. Consider a differential equation of the form d square y by dx square plus p dy by dx plus q is equal to r. Where p and q belongs to r. So this equation is second order linear differential equation with constant coefficient, and in particular it is homogeneous because right hand side capital X is equal to 0. So what is fundamental theorem for homogeneous differential equation? If y1 of x and y2 of x are any two linearly independent solution of equation 3, or any two linearly independent solution of equation 3, then the general solution of this equation 3 is given by y is equal to c1 y1 of x plus c2 y2 of x, where c1 and c2 are arbitrary constants. So in general, if f of d of y is equal to 0 is a linear differential equation of nth order, then its general solution is given by y is equal to c1 y1 plus c2 y2 plus c3 y3 up to cn yn, where y1, y2, y3 up to yn are n linearly independent solution of f of d of y is equal to 0, and c1 to cn are n arbitrary constant. Now this solution, that is y is equal to c1 y1 plus c2 y2 up to cn yn of f of d of y is equal to 0 is called complementary function. Complementary function, and in short it is written as CF, and it is denoted by y suffix c. So the complementary function y suffix c is equal to c1 y1 plus c2 y2 up to cn yn, and hence the complete solution of f of d of y is equal to 0 is y is equal to yc, or y is equal to complementary function, where complementary function is c1 y1 up to cn yn, where y1, y2 up to yn are n linearly independent solution. Rules for finding the complementary function. Consider a differential equation of nth order with constant coefficient, that is homogeneous. F of d of y is equal to 0, where f of d is p naught d power n, p1 d power n minus 1 up to pn, where pi belongs to R. Now to find complementary function, define auxiliary equation. Define auxiliary equation, that is f of m is equal to 0. So f of m is p naught m power n, p1 m power n minus 1, p2 m power n minus 2 up to pn is equal to 0. Now this equation is polynomial equation of degree n in m. Therefore, there exist n roots, and these n roots may be of 4 different forms. So the type 1 or case 1, when roots are real and distinct. Let m is equal to m1, m2, m3 up to mn be the n roots of auxiliary equation. These are real and distinct roots. Then the complementary function is given by or written as y suffix c is equal to c1 e power m1x, c2 e power m2x, c3 e power m3x up to cn e power mnx. For example, consider a differential equation d cube y by dx cube minus 4 d square y by dx square plus dy by dx plus 6y is equal to 0. Now this equation is homogeneous linear differential equation of third order with constant coefficient. Now its complete solution or general solution is y is equal to complementary function. Now to find complementary function, define auxiliary equation f of m is equal to 0. So in this case, f of m is m cube minus 4m square plus m plus 6 is equal to 0. M cube plus 4m square plus m plus 6 is equal to 0. So it is cubic equation in m. So there exist 3 roots. Then we will get m is equal to minus 1, 2, 3. Now these roots are distinct and real and distinct. Therefore, the complementary function y suffix c is equal to c1 e power minus x, C2 e power 2x, C3 e power 3x. And hence the general solution of given differential equation is y is equal to yc, that is y is equal to c1 e power minus x, c2 e power 2x, c3 e power 3x. Now by fundamental theorem, the linearly independent solutions are e power minus x, e power 2x, and e power 3x. Now case 2 or type 2. When roots are real and repeated. Let m1 be the root of auxiliary equation repeated r times. Then m is equal to m1, 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 m1 r times, and the next root is mr plus 1, mr plus 2 up to mn. Now since m1 is real root repeated r times, the part of complementary function y suffix c is written as c1 plus c2x plus c3x square up to cr x power r minus 1 e power m1x, and for remaining real and distinct roots, c r plus 1 e power m r plus 1 of x up to cn e power m n x. So if we observe this equation or this solution, the linearly independent solutions are e power m1x, x into e power m1x, x square into e power m1x, and nth linearly independent solution is e power mnx. And complete solution or general solution of differential equation is y is equal to yc. Now for example, consider a differential equation y triple dash minus 4y double dash minus 3y dash plus 18y is equal to 0. So again this equation is homogeneous linear differential equation of third order with constant coefficient. So here f of d is d cube minus 4d square minus 3d plus 18. Therefore, auxiliary equation is m cube minus 4m square minus 3m plus 18 is equal to 0. Then we get roots as m is equal to minus 2, 3, 3. So this 3 is repeated twice, that is r is equal to 2, and the distinct root is minus 2. Therefore, the complementary function is written as y suffix c is equal to c1 e power minus 2x, that is with respect to this minus 2, and with respect to this repeated root which is repeated twice, the part of complementary function is c2 plus c3x e power 3x or complementary function y suffix c is equal to c1 plus c2x e power 3x plus c3 e power minus 2x, and hence complete solution is y is equal to yc. Now type 3, when roots are complex conjugate. We know that the complex roots exist in pairs, that is conjugate of each other. Let m is equal to alpha plus or minus I beta be the root of auxiliary equation f of m is equal to 0. Let alpha plus or minus I beta be the root of f of m is equal to 0. Here alpha is called real part and beta is imaginary part of these roots. If alpha plus I beta is root, then alpha minus I beta is also root of auxiliary equation. So in this case, the part of complementary function y suffix c is equal to e power alpha x, that is real part, of c1 cos beta x plus c2 sin beta x. So if roots are complex conjugate, then the complementary function is e power alpha x of c1 cos beta x plus c2 sin beta x, where alpha is real part and beta is imaginary part. For example, consider a differential equation d cube minus d square plus d minus 1 of y is equal to 0. So again it is homogeneous linear differential equation of third order with constant coefficient. So its auxiliary equation is m cube minus m square plus m minus 1 is equal to 0. m cube minus m square plus m minus 1 is equal to 0. Now since it is cubic equation, there exist three roots. So these three roots are m is equal to 1 and plus or minus I. One is real root and other two are complex conjugate. With real part, alpha is equal to 0 and imaginary part beta is equal to 1. Then the complementary function y suffix c is c1 e power x plus e power 0x c2 cos x plus c3 sin x, which is equal to c1 e power x plus c2 cos x c3 sin x, and hence complete solution is y is equal to yc. Complete solution is y is equal to yc. Now, type 4, when complex conjugate roots are repeated, or repeated complex conjugate root. For example, let m is equal to plus or minus I beta be the complex root of auxiliary equation repeated r times. let m is equal to alpha plus or minus I beta be the root of an auxiliary equation repeated r times. That is alpha plus I beta repeated r times alpha minus I beta repeated r times. So total number of complex roots are 2r. 2r, and with respect to each independent solution, we must consider one arbitrary constant. So the part of complementary function when complex roots are repeated is given by y suffix c is equal to a1 plus a2x plus a3x square up to ar x power r minus 1 cos beta x plus b1 plus b2x b3x square up to br x power r minus 1 sin beta x multiplied by e power alpha x, or e power alpha x of a1 plus a2x plus a3x square plus ar x power r minus 1 cos beta x plus b1 plus b2x plus b3x square up to br x power r minus 1, where a1, a2, a3 up to ar and b1, b2 up to br are 2r arbitrary constant because this complex conjugate root is repeated r times. Now, for example, consider a differential equation d4y by dx power 4 plus 18 d square y by dx square 81y is equal to 0. In terms of differential operator, now this above equation or this equation can be written as d power 4 plus 18d square plus 81 of y is equal to 0. Therefore, f of d is d power 4 plus 18d square plus 81, and hence auxiliary equation f of m is equal to 0 is m power 4 plus 18m square plus 81 is equal to 0. Now this is biquadratic equation in m or polynomial equation of degree 4 in m, and its four roots are m is equal to plus or minus 3i repeated twice. That is complex conjugate root repeated twice with real part alpha is equal to 0 and imaginary part beta is equal to 3. So complementary function is given by y suffix c is equal to e power 0x c1 plus c2x of cos 3x c3 plus c4x of sin 3x, or c1 plus c2x cos 3x c3 plus c4x sin 3x. Now this is all about finding complementary function depend on nature of the roots. There are four types of roots. One is real and distinct, real and repeated, complex conjugate, and complex conjugate and repeated. And there is one special case of real root. That is, if roots are irrational. if roots are irrational. That is special case. It is not necessary special case because all irrational are real numbers. Now special case when roots are irrational. Let m is equal to a plus or minus root b. Remember, these are not complex conjugate root. These are irrational root. A is called rational part and root b is called irrational part. If a plus root b is root, then a minus root b is also a root of auxiliary equation. So let m is equal to a plus or minus root b be the root of auxiliary equation. Remember, a is rational and root b is irrational. Then the complementary function y suffix c is equal to c1 e power a plus root b of x plus c2 e power a minus root b of x, because a plus root b and a minus root b are real numbers. That is c1 e power m1x plus c2 e power m2x. Or in terms of hyperbolic, complementary function is given by e power ax c1 cos hyperbolic root bx plus c2 sin hyperbolic root bx. I'll write it as c1 e power a plus root b of x plus c2 e power a minus root b of x, or e power ax of c1 cos hyperbolic root bx plus c2 sin hyperbolic root bx. If roots are complex conjugate, use trigonometric ratios, that is sine and cosine. And if roots are irrational, then use hyperbolic function, that is sine hyperbolic and cos hyperbolic. For example, solve the differential equation d square plus 4d minus 2y minus 2 of y is equal to 0. So here f of d is d square plus 4d minus 2. So auxiliary equation is m square plus 4m minus 2 is equal to 0. Therefore, roots are minus b plus or minus b square minus 4ac by 2a. So, m is equal to minus 4 plus or minus root 24 by 2. So, minus 4 plus or minus 2 root 6 by 2, or minus 2 plus or minus root 6. So your roots are not complex conjugate, they are irrational. Minus 2 is rational part and root 6 is irrational part. So in this case, complementary function is given by y suffix c is equal to c1 e power minus 2 plus root 6 of x plus c2 e power minus 2 minus root 6 of x, or y suffix c is e power minus 2x c1 cos hyperbolic root 6x plus c2 sin hyperbolic root 6x. Hope you know how to find the complementary function. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.